Okay, I plan to continue today what we started last time. I will continue to talk about grass mining. Let me show you again the picture which we stopped last time. We have a Plaby graph. It can be here. I assume that actually the graph is bipartite and planar, and also we assume that I assume that all border vertices are white. Here. We calculated the partition function of dimer configurations. To be more precise, we can perfect matchings. We calculated the partition function of perfect matchings with boundary. It means that for any internal, we computed this. We looked at all matchings such that any internal point is included, and given number of the boundary points is also included in this matching. For example, here delta 1, 2 is a partition function for matching, such that on the boundary we take 1 and 2, and we take all internal points, vertices, this and this. And there is only one such matching, which consists of these two edges. Therefore, the weight of the corresponding matching is 80. Similarly, we computed all other matchings. The most difficult one you see is here. So here we take 2 and 4. We can take boundary vertices 2 and 4, and all internal vertices. In this case, only 2. And consider all such sets of edges which connect this, which are adjacent to these vertices. So we have one set and another set. Okay, we computed all these partition functions, and in the end of the last lecture, we observed that these 6 minors, which partition functions which we computed, they satisfy Blücher relation. Therefore, they define a point in the Grassmannian, or if you want, even in the positive, in the affine cone of the Grassmannian. And I stated the theorem, and I plan to now to say a few words how the theorem can be proved. Okay, any questions so far? Should I recall something else? Can you hear me?
Yes.
Yes.
It's fine, probably.
Sorry. Do these variables on edges, can they be identified with something we saw in previous lectures?
For example?
Don't know. We had some edge variables when we had this polygon, and we related also some variables to edges. But this seems different, but
what polygon? Maybe I forgot.
For
Grassmannian 2n or?
yes, probably yes.
For the Grassmannian 2n, like here, the edges which we have in this triangulation, they correspond to faces of the bipartite graph. So in terms of the bipartite graph, variables which we assign to sides and diagonals of the polygon, they are face variables. Okay.
Okay, so these variables, the last variables which theorem is about, is like x variables or what? if for Grassmannian, this was like a variables. We had some. Okay.
If it minors are usually a variables, yes.
But here we have parameterization of this a variables by this a, b, c, d, e, f.
Yes, we have parameterization.
Okay.
I can say that A, B, C, this A's, how to say, these 6 H weights, they are not, there is some group which acts on them. For example, you have 2 internal black vertices, and you can rescale A, B, C by some lambda, and rescale D, E, F by lambda inverse. And this doesn't change your all minors. So these H variables, they are not actually coordinates. There is usually there is something gauge freedom on them. Coordinates are usually some sort of phase variables in terms of bipartite graph.
Okay, but is this map surreactive then?
It depends on your Plaby graph in principle. For generic Plaby, if Plaby graph is say empty, then the map is more or less empty. So if your Plaby graph is like this, then you have only dimer configuration for some specific starting points. Other questions? Can you say something again? I tried to switch on my dynamics just to see how it works.
Something.
Okay, thank you. Okay, so and now I say a few words about the proof of this theorem, and then I I will return to I will talk about Poisson brackets. But there are maybe different approach to the proof of this theorem. I would like to highlight slightly the approach through the Castellane matrices. There is a following theorem due to Castellane. Let G be a planar graph bipartite. With black vertices B1, Bn, and white vertices Y1, Yn. Then exists a matrix K of the signs n times n, such that Kij is equal to plus minus weight of the H from I to J. Such that determinant of K is equal to over D perfect matchings. Weight of D. So we have n white black vertices and then white vertices, and we can construct the matrix of the size n times n, such that on the intersection of i's and j's columns, we see weight of the h from I to j. For example, if there are no edges, if there are no edges from I to j, then Kij is equal to 0. And if there are several edges, then here is yes. Then they have there is we take summation of their weights and multiply by some sign. And if you compute the determinant of this matrix, then each term will determinant of k is equal to summation over what? Over some permutations, weight of weight of 1 sigma 1, weight of 2 sigma 2, and so on, with some sign. So in this sign has two sources. First of all, we have sign of the permutation, and second of all, we have signs because signs due to Castellan signs. And the theorem says that the sign that actually this we can choose Castellan signs in such a way that this is equal to just sum over d weight of d. Or so the another just equal to this summation equal to this. Copyrighted. So these signs should be plus by 0. This is the meaning of this. Okay.
So
Yes.
I'm not going to prove.
the proposition is that we can.
Here, okay.
Sorry, can you hear me?
Maybe can say
Okay. So you can. Or
okay. Let me, for safety, just change the source of the sum. Can you hear me now?
Yes, and can you hear us?
Yes. Okay. This is for sure. Okay.
Yeah, so sorry, I asked what is the proposition is that we can find signs of weights such that there will be only pluses in this decomposition of determinant, right?
We can find these signs such that in the decomposition determinants there will be no signs here. This is Castellan theorem. Okay.
So complexity is that we have like n signs and n factorial permutations. So it's not evident that we can.
We have
form.
n square signs if you want to be precise, but still.
Okay. I see. Thank you.
And here, the fact that the graph is planar is crucial. This is not a theorem for abstract graph. Perfect match is defined in terms of the abstract graph. But, for this Castellan story depends on the embedding. And it is important that it's embedding to the plane and not to the, I don't know, genus G surface. Any graph can be embedded on some large genus surface, but it will not, the theorem will not work. For plane, it works. Okay. This is Castellan theorem. I don't know, probably I will give a hint and leave it as a problem. Whatever. And I will need another theorem of the same, also by Castellan, variation theorem. I can copy. Again, G is bipartite graph. Which is with boundary. Embedded in a disk. Such that all boundary vertices are white. Suppose we are under these conditions. So number of black vertices in G is n plus k. I copy this and you will see. Number of black vertices is in G is some n plus k. Number of internal vertices is n capital, internal white vertices, and number of boundary vertices is n small. Then exists matrix K now of the size n plus k times n plus n, such that the similar properties holds. Kj is a plus minus weight of the h from I to j. And such that, and for any subset I from the set any subset of the boundary set, let ki delta I is equal to determinant of ki. Here I is a subset of the boundary sets of the size k. So delta I is a summation of weight of d. D is a perfect matching with boundary A. Perfect matching. and ki is a submatrix of the matrix K, which have all arrows and columns labeled by 1n. And then, so we have a matrix of the size K is a matrix of the size n plus k times n plus n. We choose first n columns, and then from this set of the boundary, we choose subset of the size k. And then this set of the quasi. Then we get this score. For example, if n small is equal to k, then in order to have perfect matching, we have to pick all boundary vertices. And this theorem just reduces to the previous one. But in principle, this is a generalization. Straightforward, but still. Maybe I can support it by example here. At least I try. I didn't prepare it, but I think now it will be good. Example. We can take matrix K. And now let us write it just first of all without thinking about signs. In order to write it, I have to label my black vertices. Okay, this will be 1 black and this will be 2 black. Therefore, the matrix elements should be, here will be A, here will be B, here will be 0, here will be C, up to signs. I will I have to think about signs in a minute, but here will be 0, here will be D, from 2 to 3 we have F, and from 2 to 4 we have E. Okay, now let us look, do we actually need some signs? I think we need. And we need sign here. And after that, I believe this will agree. Okay. We can corollary. And this corollary is just the theorem which is stated above. That this delta I satisfy defines point in Grassmann. Okay, proof. Applying row operations. Okay, can be transformed into the following form. Identity n 0 something L. maybe before this, I should comment the following. If there is, if all delta I values, then okay. Otherwise, determinant of the sum ki is not equal to 0. Hence, first n columns are linearly independent. Hence, we can apply row operations. We can make them in this way. And now let me recall that Ki is a matrix in which I take all rows and first n columns and also some columns from here. So determinant of hence determinant of the Ki is a determinant of the L. We can take for L, we take all K rows and I columns. And this is delta I. So we define, and L is a matrix of the types K times N. So L defines a point in the affine cone of the cross line. So these are Plücker coordinates. And matrix L. Yes. Okay.
So, sorry, what is L here?
L is this part of the matrix K after the operation which moves first n columns of K to identity. I apply row transformations, row operations to the matrix. It doesn't change any of this determinant. By row operations, I mean I can permute them, I can add them, and so on.
So, sorry, we use only row operations or
Yes.
also?
Yes,
Okay.
we use only row operations.
So this means that we have this like how to say?
Sorry, was it a question?
I don't understand why we how it follows from the fact that determinant Ki is not 0 that we can use only row operations to find this form. I mean that like our independency like live in first n columns. We use it, as I see.
First n columns are linearly independent. Why? Because there is a choice of the K additional columns, such the resulting matrix of the types n plus K times n plus K is non-degenerate. Its term is not 0. In particular, it means that hence first n columns and k additional columns, some k additional columns from here form a basis in n plus k dimensional subspace. In particular, first n columns are linearly independent.
Okay, okay.
Permuting, then you can safely assume that this minor is not zero. You can say then using and moreover, you can assume that this number is not zero, this minor is not zero. This using row transformations, you can make it identity. This part.
Okay, thank you.
I wanted to prove something today, not just take. And this is what I want. Okay. This is a relation between another relation between Liebig graphs and Grassmannians. The fact that you have actually two relations, so the one is through dimer partition functions, and another, I assume that almost everybody forgot, but I remember we discussed last time something through zigzag passes. It is somehow resembles two stories we had for double Bershtein cells, one through factorization schemes and another again through zigzags. And so in this sense, this formula should resemble something which we had in terms of factorization schemes. In principle, I can even show, if you want, there was some factorization schemes like this, and here we also had weights on the edges. You see, actually, horizontal edges had some weights, and vertical has vertical weights are equal to 1, and ratio of the edge weights will equal to some phase variables. And probably you remember that factorization schemes are closely related to the Poisson structure. So for this reason, now I will go to Poisson structures. So what I said here, to the analogy. This leads to Poisson structure. What is the Poisson structure on the Grassmann? Let me recall that first of all we have a Poisson structure on the group. So here G belongs to GLN or PGLN. It is not very important. P in bracket GL. R is a classical R matrix, which I defined. I believe in lecture 5 or lecture 6 joint note. In terms of the matrix elements, the matrix G, this Poisson bracket reads as follows. So it is quadratic. We can take the bracket of 2G, we obtain something product of 2Gs. But it is not cluster. So here in these two matrix elements, the indices are permuted. We have I G prime, I prime G, and coefficient is equal 1/2 of the sum of two signs. So in particular, if one of the signs, one of the indices is the same, for example, G1, we compute bracket of the matrix elements on the first row. Then this sign I prime minus I is equal to 0. And hence on the second sign remains, we get sign, we get 1/2. And here will be G1 G, G1, G prime. I permuted them because they're the same. So in this case, this is like cluster bracket. Bracket of two variables is equal to their product with some coefficient, but not actually not good. But this coefficient is not integer; it's half integer. So like cluster bracket for frozen variables, and we will see something like this very soon. Okay, let me return to the Grassmannian. Grassmannian Kn is a quotient of the GLN by the parabolic subgroup. Let me take quotient from here. I forgot, do you have a favorite convention? Maybe I'll change my, I don't know what's my favorite convention here, so maybe I will have to change it at some point. What and P is a group of such matrices. So Grassmannian is a set of k dimensions of spaces and dimensions of space, and this group is written preserves n minus k dimensions of space of last coordinates, but this is some sort of just some duality. Let me think 1 minute. Okay, I prefer, maybe I will stay on such convention. In coordinates, we can write the generic G has the following form, has the following decomposition. We have something here. To follow something notation, so I want to look in. I want, but without success. Some blocks times matrix. Here have identity of size k by k, 0 identity of size mk times mk, and some unknown some matrix y, matrix A, y. So matrix elements of y are coordinates the coordinates on open cell in Grassmannian. In other words, we take a submatrix of G, which consists of first k rows, and multiply by k by k matrix W11, so that the first k by k minor of G is equal to identity matrix, and the remaining part is which is denoted by y. In particular, one can easily see that y AB is determinant delta 1k delta 1k yes, and here delta 1k without a. Maybe I can write as follows: delta 1k, a subject of replacement a to b. In this submatrix, the rows are labeled from 1 to k, so a from k 1 to k, and columns are labeled from n minus k plus 1 to n. So, how to say again? So the Gassmannian is what is a we take a set of matrices times k times n and take the quotient with respect to GLK, which acts on multiplication from the left first. Generic matrix can be reduced to this form, and these y's are coordinates. Coordinates on the affine cone of the Gassmannian are minors. So delta is delta ij is a determinant of the submatrix of the GH. And these y's are certain ratios of these coordinates. Okay. Okay, theorem. P is Poisson Lie subgroup of G. Hence, homogeneous space has a natural Poisson structure. Maybe it's better to organize it this way. So this is a theorem and this is corollary. And by word natural, I mean the following. So we have a map projection pi from G to the homogeneous space. And we take a star of pi. So this is pi, this is a Poisson pi vector. There's when we can take direct image. In principle, it could be how to say, this direct image is not could be ill-defined because for one point here, many points from G can have the same image. So it isn't clear that this pi star of pi depends only on the point on the image, but not on the point on the image. But the theorem says that this is well defined. So we can actually compute the Poisson bracket. Or in the other terms, okay, equivalently, for any two functions, f and g functions on, okay, let me write C means that they are rational functions, but this is not important. This is algebraic. Okay, this is not important. They can be smooth functions or whatever. This is differential geometric property. We can take the pre-images pi star of f, pi star of g, and compute the Poisson bracket. And property that this Poisson bracket is some rational function of g, and this function will be pi invariant. Hence, so this Poisson bracket computed on g exists well-defined Poisson bracket f and g on the quotient. I suggest the Poisson bracket on g of these functions is an inverse image of the Poisson bracket. Okay, this general definition, one can ask, can this lead to some concrete formula? This it can, and problem, which I want to review that if you compute Poisson bracket of matrix elements of this matrix Y, maybe it would be the upper indexes, because in any point I can consider minus. Then Poisson bracket of y a b and y a prime b prime is equal to 1/2 sine a prime minus a plus sine a prime minus b over product in permuted indices. So, and I want to stress that this formula is actually the same as we have here. But so actually, this can think about this formula as a formula which defines product Poisson bracket on space of matrices, not necessarily square. Not it is in principle on this formula. It is there is no need that I and j run to the same set of indices. It can be rectangular matrix, it can be anything. So this is actually formula Poisson bracket on matrices. Of course, it depends on what kind of properties do you want. So if you want just to have Poisson brackets to have which should satisfy Jacobi identity, then this formula works for any set of indices. If you want this to be Poisson-Lie bracket, so it should agree with the Lie group structure. For this reason, you have to impose that I and G runs to the same set of indices. But if you think just about Poisson bracket, it's okay. And here you get it again. Okay. This is good. And also, I was somewhere additional formula if you want to write. How much time do I have? Oh, I have like 40 minutes. Maybe it's okay. This is a formula for the Poisson bracket of the just matrix elements. I will actually need some formula for the minus of the matrix Y. First, let me write the something about the minus of matrix Y. they equal. Let me recall that we have here this decomposition. So we take now, if we take here some element, some set A1, AL, we can add remaining elements from here and get a K by K matrix. So this is equal to, again, to ratio of two determinants. In the denominator, we have 1K, 1K, and in the numerator, we have 1K, 1K, and then similarly, we should substitute all AI to BI. And in principle, here could be some sign, which I don't want to look carefully now. In principle, this gives us a formula to compute Poisson bracket, or you can compute it from the first. I will need some lemma about some special Poisson brackets. Let me say the following. So you see this formula is again quadratic, but not clustered. Again, if you look at, for example, to y's which correspond to some arrow, some column, the corresponding bracket will be clustered, but in general not. But there is a certain subset of the y's and their minus, such that the Poisson bracket between them is clustered. And actually, not only the subset is not unique, there are many such subsets. And as you can easily guess, they are related by mutations. Actually, existence of such subset was one of the original motivations of the cluster algebras. People knew that there are certain set of functions which are almost commutative, which and after quantization, they again form some sort of quantum torus. People knew this, and then cluster algebra is some formalization of the relation between these subsets. Anyway, I will introduce only one subset here, and in order, I will need to do something in order to write down their brackets. I will need some notation. We will say that A prime is less than certain set A1, AL if A prime less than AI for any I. Similarly, we will say that A prime is greater than set A1, AL we will also use notation. Denote sign of A prime minus set A1 AL to be 1 if A prime is greater than this set, minus 1 if A prime is less than this set, 0. Who can guess in which case we have 0?
It's written.
Is what?
It's written. Otherwise,
no. 0 if A prime belongs to this set, and otherwise is undefined. Okay, now lemma. How to state it? If sine a prime minus a1 al and sine of another b prime minus b1 bl are defined, and sum of these two sines is less than 1. Then
Sorry, sorry, you mean this is 0?
sorry, less than or equal to 1. Then Poisson bracket of y a prime b prime. Maybe I'll write in opposite direction. Y a1 al b1 bl y a prime b prime is equal to 1/2 the sum of sines times the product. Okay, I have to do something to move to have a bit space. Times the product b1 al b1 bl y a prime b prime. Okay, proof. Maybe not full detail, but anyway. So let us assume for simplicity that b prime belongs to set b1 bl. This condition means 1 with the same as 0, so we can assume like this, and assume again for concreteness that a prime is greater than set a1 al. Then let us compute the Poisson bracket y. We can write down this determinant by definition and use this formula. So we get a summation of P in Q from 1 to L minus 1 power P plus Q, bracket of Y A L A P B Q by A prime B prime, and here we get a remaining set, which is A without P, B without B, BQ. Maybe I should introduce this notation from the very beginning. So this set, let me denote by A. And this set I will denote by B. And this notation will save me much space and time. Similar for B. Here will be A. Here will be A. Here will be B. A. B. Okay, anyway. Okay, now compute this bracket. This is equal to 1/2.
So, sorry, why is this is true previous equality? No. When we compute YAB and YA prime B prime.
YAB is determinant of the YAP BQ. It's terms of the times L times L. We use Poisson property. So the bracket. So it is combination of the products, and bracket with this product with this is a bracket of one term with everything else. So for example, if L is equal to 2, then here we have bracket of what? Y A1 B1 A2 B2 minus Y A1 B2 B2 B1. It is equal to sum of 4 terms. So for a term like this, plus other terms. That's what is written above. Okay.
Okay.
You are not satisfied. Right.
No, I think why we have we have probably decomposition of how to say determinant, and okay, I thought we should have more terms in.
Okay, maybe I use the following. So if you take the determinant of the derivative of determinant of the matrix with respect to some matrix element, it is a adjacent minor.
Okay.
I'm sorry.
Yes. Okay. I'm satisfied with this formula.
Okay. Now we have to write down formula with signs. So this is equal to, we have two terms. So again, sum of P and Q. First we'll -1 and some power P plus Q. The sign of what of A prime minus AP plus sine over B prime minus BQ of now well, I'll write it as a sum of two terms. So A prime minus AP we have here, then Y prime Y AP. Sine and now this is equal to 1/2 sum. Here we can take summation over P. Yes, we can take summation over P over Q. We can take one summation, say sine A prime minus AP with -1 power P, and here we have -1 power Q times this term, and this will be equal to determinant of A, and here will be B without BQ, but with B prime. And for the second term, we get, I'm not 100% sure about signs, but let us ignore this. We get similarly, we get Y A prime BQ, and here we'll get Y so here take summation over P maybe, yes, here should be some Y. So maybe I was wrong here. So here should be A, here A without AP, but with A prime. And here will be opposite. A, B without BQ. Yes. So I can I look to one of the sum as a decomposition of determinant with respect to row. Now note that for if BQ is not equal to B prime, then this minor is equal to 0. Since it contains two columns of the same number. B prime is contained in B, we deleted BQ and added one more B prime. If BQ is equal to B prime, then happily the sign is equal to 0. So hence, this whole sum, the second term is 0. And for the first term, let me note that y a with a prime, b with b prime is equal to 0. Again, for the same reason, we have the same two columns. And this is equal to y a prime, b prime, y a b plus some signs. Let me ignore them for the moment. A p b prime, y a without a p with a prime b. So we have, so this sign a prime and a p is equal to 1, as we assumed from the very beginning. So this is not important, and this sign is minus 1 power p plus 1. So all this sum is actually equal up to some equal to this term. Hence, the bracket which we are computing, y a b y a prime b prime is equal to 1/2 of the product. Okay, this is some computation. Maybe it was wrong idea to prove it just on the blackboard, but let me believe that. Let us believe that some computation works. Corollary of this theorem, of this lemma, is the following. Consider the following minus y as the number of rows will be some last L rows, chi minus L plus 1, k. And the number of columns will be just some consecutive columns. Just okay, maybe I prefer to before writing formula, I prefer to draw a picture. So this is my matrix y, k, l. We take some number, some element here, and take the corresponding rectangle square. So it is so consider y's which have either this form or it can be that the corresponding rectangle is of this form. This form or this form. And this y satisfy cluster type Poisson bracket. And as a problem, I leave find coefficients. So by word cluster type, I mean that we can, if you take the bracket to y and y prime, we get some number times y and y prime. And this coefficients follow from this lemma. But I think I have like 10 or 12 minutes. So, and I plan to plug to Bershtein graph, so better to not compute this explicitly. This is certain subset of the Plücker of the coordinate on the Grassmannian, which has good Poisson brackets, and just by definition, by computation. Okay. So this is what to take away. We have some good subset of the coordinates. Okay, now let us return to the story about Plug graph and consider bipartite graph. Okay, and now I have to copy from my notes some picture. I have many pictures. Okay, let me copy this. So this is an example of the Grassmannian 3-7. Okay, these computations maybe not. I will explain them in a minute, but before this, let us look first. Let us look to the picture. So for we have this Grassmannian 3-7. All internal faces are hexagonal faces. This is a bit. In principle, you can shrink these two valent vertices and get and these two valent vertices and get foregons on the boundary. But picture maybe looks more clear if all the boundary faces are hexagonal. All internal faces are hexagonal. And we have edges from the boundary to the border. We have vertical and horizontal. And in total, we have in total we have this Grassmannian 3-7. So we have 7 boundary points. 3 of them are here, which they correspond to horizontal edges. 4 correspond to vertical edges. Okay. Now,
sorry, they will be hexagonal in any case, not like 3-7 and.
Yes, there is hexagonal side 2 times 3. 2 is 3 minus 1, and another number is 4 minus 1. 3 times. Actually, we had corresponding, quiver 2 lectures ago, but maybe I will not stress this now. Xij is a monodromy of the phase. Now I come from h variable to phase variables. So monodromy is computed counterclockwise. And I assume that edges are oriented from black to white. I'm not 100% sure that this agrees with some convention which I had before, but whatever. And for this variables, we have cluster Poisson bracket. So it means that in principle, if we have 2 vertices which are connected by such h, here x and x prime, then Poisson bracket of x prime and x is equal to x prime x. So my standard convention that edges of the quiver goes clockwise around black vertices and counterclockwise around one vertices. The only thing to point out. Okay, let me move. Where is this picture? That near the boundary we have frozen variables, and usually in case double Brea cells, in this case Poisson bracket becomes not integer, half integers near the boundary. We have, so if we have on the all boundary vertices are white, so we have boundary, we have some h. And in this case, this bracket is equal to 1/2. And maybe this is explanation, this is part of the proof, but before the proof, I state better to state theorem. The cluster bracket coincide with Skляnin bracket on the Grassmann. So what bracket which we had in this slide, in which I made some computation, it comes from the scaling bracket on the group, a matrix bracket on the group. And this, for this reason, I call it scaling bracket on the Grassmann. On the other hand, we have a map from the to have a map to the Grassmannian map, which depends on the age variables, on the age weights. If you look at the map to the Grassmannian, it is actually depends only on the phase variables, on the monodromies around the phase. So remark. So if you consider ratio of two minors, so this depends on phase. Hence, this statement makes sense. So we defined, I here defined brackets on the phase variables, which are actually a cluster X variables, and their ratios of the minors, and yes. So this can be expressed through the X variables, and therefore we can compute the bracket. Okay, I have to stop very soon, so let me explain it just a bit on this picture and left everything else in problems. So first, what I want to explain here that these deltas are dimer partition functions. And the very first dimer partition function, it corresponds to the points 1 to 3. So let's start with the proof. First, let me know the delta 1 to 3 or 1 to k is a monomial. In this, so there's only one dimer configuration which takes from the boundaries these three, and in general k this k vertices. Indeed, one have to pick them. One have to take this 1 to 3 like this, and then what? This vertex have valency 2, but this black is already used, so we have to take this arrow. Hence, we have to take this, and this. So therefore, we have uniquely determined h from this, and so on. So this is just a monomial. But moreover, if you take, for example, delta 1 to 4, then this part remains the same. And for vertex 4, we have to pick this h and this h and this and this and this. So the ratio of the dimer configuration of 1 to 4 and 1 to 3 is just X variable. So we can actually prove that some particular set of these deltas, they are monomial in X variables, and this exact for their bracket is cluster. And this set of deltas coincide with set of y's which we constructed above, for which bracket is also cluster. So these two stories agrees, and theorem is proven. Okay, I think I'm out of time, so I finish, and maybe I'll write. I like the theorem. I'll write more about it in problems. Questions?
I don't understand what how this xij related to y's which we have before had before.
Mm. In principle, from the first law, they are unrelated. But on the second, what we have, this x, as I stated in this proof, that so in principle, this theorem, if we take any bipartite graph, they're unrelated. But we choose some very particular bipartite graph, and for which this x is the ratio of the dimer partition functions. So the ratio of the Blücher coordinates. And these y's which we have here, they are also ratios of the Blücher coordinates. So it appears that at the end of the day, they coincide for this particular graph. But in general, I don't know, y's are defined only for this particular graph. For this particular set of minors which we put in the y, they are cluster variables, and this means that they are phase variable to certain Liebig graph.
Okay, thank you. And about I wanted to ask about Poisson structure before. We have like this. We have this Poisson structure, and we can ask what are symplectic leaves and how this map to Grassmannian. How to say, what will appear if we restrict it to the symplectic leaves?
In general, symplectic leaves will be quotient by a certain subgroup. So I mean, we have generic symplectic. We can take the larger generic symplectic leaves, and they are quotient by parabolic subgroup, maybe some part of the parabolic subgroup. But there is also some very particular symplectic leaf for which so this one more story that actually Grassmannian can be viewed as a quotient of the double Brias cell by an important subgroup. So in this way, you can reproduce this coordinate from the coordinate of the double Brias. So one can think about Grassmannian as a quotient of some certain special symplectic leaf, a set of symplectic leaves. Other questions?